Charlotte Kirchoff-Lukat.
Yeah, thank you very much. Thanks to the organizers for putting on this wonderful event. I'm really enjoying myself. So what I'm going to talk about here is part of this larger research project with this name funded by the European Union. So if you want to know more about the sort of general scope of where I'm trying to eventually go, you can visit the website. So today I'm going to zoom in on the particular sub-project that I'm working on right now. And this is about associating a Fukaya category to a log symplectic surface. And today we're going to focus on the very simplest example of a log symplectic surface, which is a certain log symplectic structure on the sphere. So since this is not a symplectic topology audience, I thought I'd give a small introduction to what Fukaya categories actually are. So this is a technique from symplectic geometry. So normally a Fukaya category is in some sense an invariant assigned to a nice symplectic manifold. And nice means there that in general, your symplectic manifold needs to satisfy some specific properties in order for this to work. And the reason, or the chief reason people study this, is homological mirror symmetry. So mirror symmetry is an idea that originally came from string theory, where people essentially noticed that different string theories on different Calabi-Yau threefolds would occasionally be isomorphic in such a way that essentially a string theory derived from the symplectic structure on one manifold gives you the same physics as a string theory derived from the complex structure on another manifold. And so homological mirror symmetry due to Kontsevich is one proposal for a rigorous mathematical formulation of this observation. And so what you do is you have a pair of manifolds, one symplectic and one complex, and you assign to each of them what's called an A-infinity category. So on the symplectic side, this is the Fukaya category. On the complex side, this is the derived category of coherent sheaves. And then we say that these different manifolds are mirror if these categories are equivalent as A-infinity categories. So we're focusing on the symplectic side, and I just want to explain approximately what this Fukaya category is. So there are a host of technical difficulties, and I'm not going to be very precise at this stage. This is just so you can get a conceptual overview. So the objects of the category should be a collection of Lagrangian submanifolds, and the morphisms between these should be their intersection points, or rather should be the Floer chain complex, which is spanned by the intersection points over some field, which for the purpose of this talk will always be Z2, but in general will have to be a bigger field than Z2. And now, of course, if I want to take this like formal sum over the intersection points, this really only makes sense if there's a finite number of them, or at least a countable number. So we want those Lagrangian submanifolds to intersect each other transversely. So a priori, morphisms are really only defined between objects that intersect transversely. And then on top of that, there's this A-infinity structure. So for an ordinary category, you'd only be expected to be able to compose morphisms. And here, in addition to composition, which is a binary operation, we have, in fact, one operation for each k larger or equal to 1 that will essentially compose k morphisms that go between the correct Lagrangians. So starting here at L1, so we first have a morphism that goes from L0 to L1. The next one, the pairing would be L1 to L2, and so on and so forth, until Lk minus 1 to Lk. And the result of this composition operation is then in L0 to Lk. And these infinitely many operations are subject to what's called the A-infinity relations. And what these essentially are in low degrees. So first of all, for M1, the operation that only takes one morphism as an argument and spits out another one in the same morphism space, the A infinity relation is simply that this squares to 0. So this is a differential, hence why I'm referring to the morphism space as the Floer complex, because it is equipped with this differential. So K equal 2 is, of course, what we would understand as the ordinary composition or multiplication of morphisms. And that has an associativity relation, except it's not exactly associative. It's only associative up to things that involve this multiplication of degree 3 and the differential. So and this sort of picture essentially goes on in higher degrees. So all the higher infinity relations are in a sense higher associativity relations up to whatever higher degree is. Now the question is, of course, how do we compose or how do we multiply intersection points of Lagrangian submanifolds? And this is done somewhat in analogy to Morse homology, where we count flow lines. Here we count holomorphic maps from the disk into the manifold, such that the boundary of the disk lands inside the collection of Lagrangians that we're looking at. So these lines are meant to be the Lagrangians. I should have maybe made a note there. So let's have a note. So this is L0, this is L1, L2, and so forth. And so for MK, this map will go from the disk with K+1 marked points. And so the edges between the points go into the Lagrangians, and the marked points go into the intersection points that we're trying to relate. And so then the sort of K-fold product of intersection points, so if it's P01, that's meant to be intersection point of L0 and L1, and so forth, is then given by a count of such polygons, where the final corner is some additional intersection point Q. So that's what we're summing over. And of course, in order for this to make sense, we need to ensure that this moduli space is zero-dimensional. And so for this, well, okay, the map is meant to satisfy an equation that's essentially the Cauchy-Riemann equation. So it's a holomorphic map. And then we need to only consider such maps of correct index, which is essentially a type of winding number. In our case, we're only going to look at 2 dimensions today. And in 2 dimensions, this is all very nice in that you're actually just counting these polygons. And the only condition that comes in, this index condition, is saying that all the corners should be convex. So it looks like an actual polygon. And so for 2-dimensional manifolds, you can literally just count these polygons with K+1 corners for the MK operation. Okay. Yeah, so that's roughly how that works. So now I don't want to talk about symplectic surfaces. That has been done before. I want to talk about log symplectic surfaces, which you might also see referred to as B-symplectic, B-Poisson, or in the original publication treating these surfaces topologically stable Poisson surfaces. So what is this? Assume we have an oriented closed surface. So this little O is meant to be a fixed orientation that we've chosen. Then a Poisson structure is topologically stable or log Poisson if it intersects 0 transversely. So on 2-dimensional manifolds, every bivector is Poisson since the Jacobi identity is trivial. And so here we're really just fixing the vanishing locus of this Poisson structure. And what we're saying is that the vanishing should be transverse, which in particular means that if we wiggle the bivector a little bit, the vanishing locus is not really going to change in any essential way, hence topologically stable. And the vanishing locus will be an embedded collection of circles. So I'm denoting that by Z and the separate circles by Zi, which divides the surface into separate connected components. And you can see I've marked these components with signs. That's simply a sign to indicate the orientation of the, so given by this log Poisson or log symplectic structure relative to the global orientation that I've already picked. So it's plus if they agree, and it's minus if they don't agree. And every time you cross a singular circle, the orientation flips. Okay, you have already written it. So when I say log symplectic form, I'm really referring to the inverse of this bivector, which is now, of course, a singular symplectic form with a log singularity on the vanishing circle. And in local coordinates around each circle, we have the cylindrical neighborhood with coordinates x and theta, where x goes away and theta goes along the circle. And then you can see that it will have this coordinate form. So there's this dxi over xi term, which is the log singularity. Whoops. Well, no, you can find different ones around every singular circle. So the question was, are the coordinates canonical? And so no, they're not. But what is actually invariant is sort of, well, okay, of course you can write it with a different constant here too. But there's actually an invariant associated to this, which is, so the modular vector field of this Poisson structure is always tangent to these singular circles, and that has a distinct period. So in a sense, there is a sort of width of the circle, of the period of the circle, that is an actual invariant, but the coordinates are not. Okay, so for our purpose, it will be important to look at the Hamiltonian vector fields of this kind of structure. And what you can immediately see is that no matter what the function is, the Hamiltonian vector fields are all zero on the singular circle. So in particular, the resulting Hamiltonian isotopies, when we integrate the Hamiltonian vector fields, leave the singular circles entirely invariant. And so in particular, if we take Lagrangian submanifolds and perturb them under Hamiltonian isotopy, the intersection with the degeneracy locus will never change. And so, yeah, as I said, we want to construct a Fukaya category. So we are interested in the Lagrangian submanifolds, which are here just embedded circles. And we want to take those embedded circles that are transverse to the singular circles Z. And we assume that they are non-contractible when Z is fixed. So in particular, essentially, there are no Hamiltonian isotopies that will in any form contract these or change their volume to something negligible. And so in particular, since Hamiltonian isotopies don't change the intersection points with Z, you can see that log symplectic surfaces in some sense have many more distinct Lagrangians than ordinary symplectic surfaces do, since with an ordinary symplectic structure, there is nothing that's fixed under Hamiltonian isotopy, so there are no fixed points under all Hamiltonian isotopies, and so I can somehow move Lagrangians around a lot more than in this setting, and that will affect what happens with the Fukaya category, because there are now suddenly many more objects that we cannot relate under Hamiltonian isotopy. Okay, so how does this proceed? First of all, we want to fix a volume form omega 0 for the surface, and then we're going to write the Poisson structure pi as a product of a function h and the inverse of this volume form. So what we're producing here is a function that precisely vanishes linearly on the vanishing circles. And we want to essentially choose omega 0 nicely so that the h that results is Morse and has few critical points, doesn't necessarily need to have the minimal number, but just it's annoying when there are too many critical points sitting around. And now what we do is that for each natural number n, we're going to pick a collection of points in the singular locus, and we're going to consider a collection of Lagrangians that is specified to intersect the singular locus only in those n points. And we're going to define that kind of Fukaya category. So the subset of Z is denoted curly Zn. And what's the time doing? Is it on 15 minutes or what am I on?
Oh, you have 10 more minutes.
Okay, good. Right, so we always choose a finite collection of points in Z and only look at Lagrangians that intersect Z there. So the point being that in order to really say anything about the A infinity and Fukaya structure of this manifold, we need to somehow be able to get a category that has a finite set of generators. And so we're breaking it down to a finite set of intersection points. But of course, if we manage to do this for every n, then essentially we have understood the A infinity structure for for an arbitrary collection of manifolds, of Lagrangian submanifolds. Okay, and so here I have given some properties that this collection of Lagrangians should have. It's not an exhaustive list. So as I mentioned on the previous page, but have not written here, we want to take only non-contractible Lagrangians. And additionally, we're now going to require that they do not intersect the critical locus of the Morse function h that we chose above, that if you restrict h to alpha, it's always Morse. This is not a very strong condition either. You can just wiggle a Lagrangian a little bit and that will make the restriction Morse. And near every point where they intersect Z, they should all agree. So essentially, we want only one direction for Lagrangians to come out of intersection points with the degeneracy locus. And finally, we need to pick a time t hat that is small. And I'm not going to say exactly what small means, but basically what this refers to is the perturbation of a Lagrangian alpha by the Hamiltonian isotropy with respect to the Morse function h. And we want to essentially make a cut of t such that this perturbation really only moves the Lagrangian a little bit in a well-defined way. And so here's a wish list of things that this construction should satisfy. And I've written almost theorem because I almost proved them, and I'm very confident that they work, but I can't claim to have a complete proof. So the first thing, of course, is that the resulting construction should actually be an A infinity category. So in particular, these A infinity relations for the operations that count polygons need to hold. Then making different choices at each step. So for example, choosing a different collection of Lagrangians with the same intersection point with Z should not really substantially change the category. So there should be A infinity equivalences if we make a different choice. And the category should end up being finitely generated, or at least finitely split generated. I'm not going to say exactly what this means. Heuristically, it means that you can somehow see the entire A infinity structure from a finite collection of Lagrangians and get the information of all other Lagrangians from your finite set. So what do we potentially need to change compared to the symplectic case? I've already said there will be now more Lagrangians and in the end also more generators, just because the singular locus, the intersection points with the singular locus cannot be changed. And then in general, the common intersection points in Z. So when we have two Lagrangians in our Lagrangian collection that intersect Z in the same point, that is a new phenomenon that we do not see in the purely symplectic case, of course. And so in particular, what we need to ask ourselves is, what about holomorphic disks or these holomorphic polygons that somehow interact with Z? And so maybe this is not, let's get rid of this layer for a moment. So here I've drawn situations that might potentially arise. So first of all, here's a polygon of Lagrangians, and the singular locus goes right through the middle of it. Should this be a polygon? And the answer is no, this is definitely not allowed. The reason being that if we study the holomorphicity condition, so basically the differential equation that arises from a log symplectic structure instead of a symplectic structure, this is most definitely never a solution and is totally forbidden. The next question is, what about sort of disks that go between points that are in the interior and points that are in the singular locus? And here it's not so clear cut. So these can be solutions, these can be holomorphic. But basically it turns out that we do not want to consider them. And we can just say, no, we are not going to allow these kind of disks. So there will never be any disks going between points that are in the symplectic bulk and points that are in the singular locus. The singular locus intersection points in that sense, so they need to be counted as intersection points. They're there, but they're entirely inert in that any A infinity operation involving them will be trivial. So that's what was shown here. They're crossed out. But here's the thing that is new and that we do want to consider. So essentially, common intersection points between Lagrangians that lie in the singularity locus should be allowed as sort of, they make little tunnels where holomorphic disks can cross from one symplectic component into the other. So here we have 5 points, and they are connected by a kind of funny pentagon that goes through this common intersection point in the singular locus and flips orientation in the process. So if we look at the domain here, so here's the disk, then we'll have this whole interval that gets mapped into this one point, and the orientation of the map is one way here where it goes into the positive symplectic component, and the other way here where it goes into the negative symplectic component. And yeah, so that's somehow the special structure that this log geometry makes arise. So I've already said that in order for these morphisms to make any type of sense, how much more? Oh, okay. We need to have the Lagrangians be transverse. And so what we're going to do here is we're going to set the morphism space to be actually the Floer complex between an unperturbed Lagrangian, and then the second Lagrangian will always be perturbed. And we look at tuples of multiple Lagrangians, like here for the kth A infinity operation. They will sort of progressively be perturbed further. So it goes here from alpha 0 to alpha 1, which is perturbed by a time t1. And then the next Lagrangian will be perturbed by a time t2 that is slightly bigger, and the next Lagrangian by type t3 that is again slightly bigger. And in this way, we can ensure, first of all, that all Lagrangians, like all pairs of Lagrangians, intersect each other transversely. And if we pick the times right, they also don't make triple intersections. And since our condition was that we pick times sufficiently small, it actually doesn't matter what exact time we take. So for sufficiently small t, these morphism spaces will, sufficiently small t, the morphism spaces will always be isomorphic. And so in the end, the exact time that you take does not change any of this. And that in the end ensures that, well, the whole construction comes out okay, and the A infinity relations hold. And now, of course, I had this entire example with the sphere, but well, 25 minutes are really short. So ask me about it in the break if you're interested. Thank you for your attention.
So what does this look like on the mirror side? Like what sheaves do you get and how does it interact with the zero set?
Right, so I haven't actually finished any type of proof for mirror symmetry, but here's an idea for what I think this should be. So there is already mirror symmetry for surfaces with nodal singularities. And what turns out to happen there is that any such nodal singularity basically makes a puncture in the mirror. And what the situation we have here is quite similar to the nodal singularity in that somehow the almost complex structures for for a log symplectic structure really look like they are in the neighborhood of a nodal singularity. So all we've done here is essentially a real oriented blow up, which means that in comparison to this situation, the additional information that we have is that we need to remember in which direction Lagrangians come into the singularity, which corresponds to what their intersection point is in the blow up. And so I think what the mirror will be is something like this, with an additional information that remembers the direction that the Lagrangian comes in.
Wonderful, thank you.
Is there anything else? No questions?
So there is in the original work of Olga Radko, she gave a classification of topological stable in terms of some combinatorial description. We're using these renormalized symplectic areas. And do you expect that you can describe the Fukaya category in terms of this combinatorial description?
Well, to some degree. So first of all, somehow the main topological information that is in the classification is, of course, the topological arrangement of the singular circles, which you can encode in terms of a bipartite graph, where the vertices are the symplectic components and the edges are the singular circles. And the Fukaya category, so since Lagrangians, are fixed in which singular circle they go through, and then also the holomorphic disks only go through certain singular circles, somehow that information is definitely, like, the topology of this graph is very visible in the Fukaya category. What I don't think is visible is either the overall volume. Well, okay, so I think the overall volume is not visible. And this is, not, in a sense, not so surprising, because in the symplectic case, the Fukaya category also doesn't really see the volume of the surface. It also only sees the basic underlying topology. And so, of course, what this regularized volume amounts to in the log symplectic case is a question of, basically gives you information of the relative sizes of the symplectic components. Yeah, and I think that just gets lost, just like the symplectic volume gets lost in the symplectic case. And I think, you could somehow say that since intersection points with the singular circles are fixed, in a sense, the period of the circle is somehow in how many positions you can have that intersect this. But in the end, the combinatorial information in the Fukaya category also doesn't really see this. So really what this Fukaya category, the information that this has, is the topology of the symplectic components and how they're connected, and not really the period and not the overall volume.
Thanks, Charlotte, again.